All right, hi guys, and this is our lecture on global wind patterns. So haven't been there with you guys, and so far, hopefully things have been pretty easy to understand. But today things get a little bit trickier, so I did want to make sure and do this as a lecture. So it's going through Edpuzzle, but obviously you're looking at Nearpod here, just because that was how I ended up doing it. I kind of had a second thought. So we're going to go through really talking about the winds, what drives the winds, tying that back into the uneven heating of Earth's surface, having a couple practice questions, which you will see in the Nearpod and you'll also see in the Edpuzzle. And then the reminder here is at the end of the semester is coming. Anything that is work through this week is going to be included. Next week is technically still part of first semester, but I'm not going to be counting those things as due until after into second semester. So again, end of the semester is coming. The end of the work that will be collected is going to be this week. And then I'll be back for a few days before we have to make sure that everything is completely and totally submitted for semester one. We'll still be doing work, but that work, the due dates will be pushed out into semester two. All right, so here we go. What we're going to be talking about really are enduring understandings that we've already discussed last week. So you see that at the bottom, it says these are really the same as last week. We're just going into more depth. So really looking at that uneven heating again, that's a huge thing that comes back over and over again. And then talking about how that's driving the climate patterns that we see around the Earth. All right. Lots of words to know. You see that right here on this list. There are a lot of words. We're going to go through them all. So you're going to get to see all these again, but definitely one of the more challenging lectures vocabulary wise, because we hit it pretty quickly and it's a lot of the basics that drive weather patterns. So for those of you who really like watching the weather, you might be more familiar with these terms than other people are. But hopefully by the end, you got it. We'll see. So here we go. Next slide. There we go. Do remember to take notes, especially because there is such intense vocabulary focus, and also because the diagrams that you see are definitely things that help to make sense of the vocabulary, and because they're things that you will see again. This unit, I would say just in general, is a lot of diagrams going from the Earth's atmospheres, and we talked about the graph showing you the temperature versus the altitude. And then what we're going to see today, again, just a lot of graphics that come up over and over again. All right, so reviewing where we were last week, what you guys learned about was the uneven heating of the Earth due to the tilt of the Earth on its axis. And that was what your gizmo focused on too. So really looking at how many, those, what do they call them? They said fire, and then you had these little bursts of sunlight out of 100, how many were going to hit the plate. And you saw that as the angle of the plate changed and became more dramatic, you were getting less hits. So it was a less intense sunlight. There definitely were still some people who didn't get all of those questions correct that were application. So I do want to make sure that you guys realize that that's the reason, that the tilt makes it so that the sunlight, it's not hitting as intense. That direct 100, let's call them watts, 100 watts per area is going to be spread out. All right, so that's why we have the seasons. But there's more to it than just that, because if it was just that, then we would expect to see the exact same temperatures, no matter sort of where you are, if you're close to the ocean versus if you're in the middle of the continent. We just know that that's not the case. So there's a lot more going on than the temperature. All right. So properties of air, and this is where we start to get a lot of those vocabulary terms. Air has several important properties that determine how it circulates in the atmosphere. So starting off, we're going to be looking at the moisture. Shouldn't be a big surprise. We talked about water vapor already when we talked about the atmosphere. So you have the maximum amount of water vapor in the air at a given temperature. That's the saturation point. If we go above that, that's when we start to get things like dew on the ground. So at night, the interesting thing is, this is why dew happens. At night, the temperature drops. And so the air can't hold on to that water vapor. And so it must release it as liquid water. So that liquid water is on our grass in the morning when we wake up because of that saturation point. Okay, so warmer air can hold more moisture. Makes good sense if you think about going to Florida. Florida air is hot, it's humid. That hot air holds on to more water vapor. All right, adiabatic cooling and then adiabatic heating. So this adiabatic. All right, so what we're talking about now is the effect that the change in pressure has on a column of air. So adiabatic cooling says it's the cooling effect of reduced pressure on air as it rises higher in the atmosphere and expands. So we think about going back to the atmosphere lecture, we say as we go up the mountain, the temperature decreases. And it makes sense because we've done that. Well, the why it decreases is those particles are getting further and further apart, reduced pressure because reduced gravity. And so that expansion is going to release heat. And now we go down the last one, so I'll go skip. Latent heat release, the release of energy when water vapor in the atmosphere condenses into liquid. So you're going to get that going on too as you get air rising up and forming clouds, condensing into those water droplets, and that's going to give you even more heat release. So cooling is going up. So when we go up, we are getting adiabatic cooling, and then we also get extra cooling because of the heat release. Now, if things expand, they get bigger, and that causes there to be cooling. Then when they fall and get closer together due to gravity, due to pressure, then things are going to heat up. There's going to be more friction between those air molecules. So this is tying together a lot of different things. If you're thinking chemistry, if you're thinking physics, yeah, it's all in there. So pressure is a big piece, and also we've got that water vapor. All right, so again, air pressure, this is huge. Warm air, by its nature, is less dense. So if I have, let's say, pollution right here, that warm air, because I'm saying pollution, so I've done something like smokestacks, maybe it's condensed water, vapor, whatever it is, but it's hot. Okay, so this pollution is hot, and we know that warm air rises. We know that because we learn in a fire, you stay low. So air is going to rise up, and that's going to generate low pressure on the ground because the molecules are going away. Pressure, really think of it as that pressure on you and the blanket that you feel from the atmosphere. So if we have the air rising up because it's hot, that's going to generate low pressure conditions. When we have low pressure, it is associated with precipitation. So if I look at that drawing on the right, that low pressure, the air is going up, but along with the air, the water vapor is going up too. And as the water vapor goes up and the air goes up, it's going to have adiabatic cooling as the particles spread out. It's going to get to that saturation point. The temperature drops low enough that it's going to condense. And then you're going to also get that latent cooling effect. The latent heat release is what it was called, the latent heat release going on with that adiabatic cooling. Lots of things going on right there. All right, as opposed to high pressure, when air is falling, or sorry, start with cold air is more dense. Okay, this is just the general properties of matter that when we have something that's cold, when we freeze something, the molecules get closer and closer together. So cold and dense go together, warm, expand, those go together. So as this cold air is more dense than the warm air, it's going to be falling. Now, as it falls, it's going to generate high pressure conditions, make you feel like you're under that blanket of the air. High pressure is therefore going to give us clear skies. So we see these on the weather map. You talk about high pressure systems and low pressure systems. And what we just had happen when we had snow last week, they weren't expecting the snow. They knew a cold front was coming in with high pressure, but there was also a low pressure system coming up and bringing moisture right off the coast of the Carolinas. They thought on, let's see, even on Sunday morning, they thought that the snow was going to stay in North Carolina and below. But they kind of got some of the other factors wrong. There's a lot that goes into weather. And that low pressure system kept moving up And that was why we especially got the moisture, if you think about on the 95 and east, because that low pressure with all the moisture was actually over the ocean. The high pressure with all the cold was coming from Canada. That's where we get our cold air. Okay, that has to do with our seasons and what you guys saw on the diagrams. All right, so this is just hopefully a fun question. I'm not even going to put it into the ed puzzle, but if you were to look at the weather, high pressure and low pressure are always on the weather maps. Not every single map, but they put them on the national weather maps. They have specific colors associated with them. And so this one is just asking you what color would you have for, let's see, this is high pressure shown capital H, low pressure shown capital L, and oh, there we go, because I can't see the whole question up here. Yeah, I'm not used to doing this anymore. I think the question basically says, what colors should they be? I'll figure out how to make this work sometime. But so what colors should they be? There you go. You can sort of see it pop there. And their colors are actually going to be that high pressure at the H. This is where students get mixed up. So should it be red or should it be blue? It's an H, but high pressure is cold air. So if you look at the weather map, a high pressure system is blue. That H is blue. The low pressure actually is associated with warm air and with stormy weather. That L is going to be red, warm, low pressure. One of the easier ways that I just tend to remember this is that low pressure is really very closely associated with storms. That's why if you grow up in Texas like I did, we had a barometer on our back porch. Thermometer tells you it's hot outside. It's Texas, it's hot. The barometer tells you if the pressure is falling, really bad weather is coming. So we watch the barometer and we can see if pressure falls, then you want to be worried about those storms. So low pressure, hurricanes, tornadoes, thunderstorms, you're going to get those cloudy skies. All right, so we have this rising and this falling of air, and it goes in a cycle. And we call these cycles the convection currents. Now we're going to have it twice in this unit. We're going to see it here 3 times maybe. We're going to see it here. We also talk about a little bit in the ocean, and then we're also going to see convection currents inside of the mantle of the Earth, and inside more specifically the asthenosphere. All right, so what is a convection current? It can happen with anything that has fluid properties. So it can be a liquid, it can be a gas, but it's this movement that occurs because of unequal heating. So if we look at this diagram, we're seeing low pressure on the left-hand side of the drawing. So low pressure means that it's warming up and the air is rising up. So hot air rises, creating low pressure. So that air is heating up as it goes up. And as that happens, the air warms and rises. I don't like the way that's right. So the air warms and rises. This is actually adiabatic cooling that's about to happen. And then you get your latent heat release. Then that air is going to condense and it's going to become closer together and it's going to fall and you're going to get high pressure. So this is the atmospheric convection currents. All you really have to remember is that when things are close to the ground, when air is close to the ground, it's going to warm up and it's going to go up. And then it's going to get into the atmosphere, cool down, and fall down. Low pressure where things go up, high pressure where things come down. All right. So this picture is starting to look a little bit more in depth. Same idea. This is still a convection current, but we're looking now, it's actually having to do with ocean breezes in this particular picture. All right, so what we see is, again, the surface creates low pressure. We've got low pressure at the surface, the surface, that heat that is contained because of the ground having a different specific heat versus the ocean. You're just going to get some low pressure. So all we got to worry about here is that heat is causing the air to rise. It rises, it expands, and that's going to make it cool down. So it was hot, and as it's going up, it's cooling down, just like the hiker on the mountain. gets up to the top, it's going to condense and we're going to get precipitation. So that low pressure side, again, is where we're going to end up getting those clouds. So we see the cloud in the picture. So adiabatic cooling, it was hot near the surface, now it's cold at the top. And latent heat release, it's releasing heat as the water droplets form. All right, other side of the picture, top of the picture. All right, so up in the atmosphere, you get that latent heat release radiating into space, and that's going to now produce that cold, dry air. Now that is going to fall back down to Earth. So now we get that left-hand side. That cold, dry air is going to, it's dry because it lost all its moisture in the cloud. That cold, dry air is going to fall down and it's going to warm up as it gets denser, closer together, more strikes, more friction. So we get warm, dry air and that high pressure system. Okay, so high pressure, I talked about it being wintertime, we were getting high pressure. You could also get high pressure in the summertime. It's just relative to one another. Okay, so higher pressure than the low pressure. When we are all in summer, then the air is all going to be warm. High pressure is going to be clear skies. It's actually going to feel very oppressive because there's not a cloud in the sky. The low pressure system you're kind of hoping for because you might get some rain and that's going to be a little bit nice, but it will be muggy. All right, so a couple questions. Let's go ahead and go through these. And that's right, I have to do it a different way. What do I have to do? I have to do... See, it's been so long because I'm doing this on mine and not yours. So here's what I'm going to do. I'll be adding the questions as I put this into the Ed puzzle. So you'll see the questions in here because right now you don't see those. Oh, can I do it this way? No, I can't do it that way. Okay. I've never recorded my own Nearpod Zoom thing. All right, another diagram for you guys. These are always put into the calendar, so you can see that or under the calendar. So if you want to come in and look at it, this is the textbook diagram, a little bit more detailed, a little bit more vocabulary focused. So if you want to see it a different way, this is there for you in the presentation as well. All right, so these convection cells happen very predictably at 6 places around the Earth. Now, they're always happening also, just because if you get higher pressure here and lower pressure here, like we might have on a mountainside, or we might have with an ocean sea breeze, land breeze. But there are some places where the uneven heating of the Earth causes this all the time. So the first one that we need to know is the Hadley cell. The Hadley cell is a convection cell that occurs between the equator and 30 degrees north, or between the equator and 30 degrees south. So I said there's 6 convection cells, but there's 3 sets of 2. So there's 2 Hadley cells. So the Hadley's air is going to get hottest at the equator, and it's going to rise up. That's why we get a rainforest at the equator. And then it's going to fall down at the 30s. 30 north and 30 south are where we get hot, dry deserts. So really important in factoring into climate and biomes. The other thing here, ITCZ, just so that you know what that is, intertropical convergence zone, latitude that receives the most intense sunlight, which causes the ascending branches of the 2 Hadley cells to converge. So this ITCZ is that spot where like the rain is highest, the rainfall is going to be highest. We're going to talk about something going on where basically there's a line that can't get crossed by these convection cells, and that is the ITCZ. We don't go much more in depth into that, but I want you guys to see what that is. So there's the Hadley cells are right next to each other, but they're mirrored, one in the northern hemisphere, one in the southern hemisphere. But depending on the time of year, that might shift up to the Tropic of Cancer, or it might shift down to the Tropic of Capricorn, depending on where we are during the summer solstice. Nope, the equinox. During the equinox, it's going to be right on the equator. Okay. All right, polar cells and feral cells. Those are your other ones. I do polar first because that's easy. It's at the poles. we're splitting the globe into sections. So 0 to 30, 30 to 60, and 60 to 90. So this polar cells are that 60 to 90 north and the 60 to 90 south or negative. And then the feral cells are the ones in the middle. Okay, next slide. This is what it looks like when you put it all together. Again, the Hadley cells are the two that are closest to the equator, and we see the arrows rising up at the equator, and with that, you're getting that rain. Now, that upward motion then makes a downward motion at the 30s, and that's where we see the desert. That down is going to be mimicked just to the north and just to the south of those cells. So then we get this downward motion, and then it's going to rise back up. So we have an area like Seattle that has rain all the time, and it's not at the equator, but it is around 60 degrees. And so that 60-degree mark is another place where we have this rising low pressure constantly, consistently. Okay, so these are what those cells look like. Again, Hadleys are the two in the middle. The ferals are the, if I was going to number these 1 through 6, feral would be 2 and 4, and then the polars would be 1 and 6. So all the way up at, say, 12 o'clock and all the way down at 6 o'clock. All right. I already went through this. So again, the warm air rises up, the dry, and so the warm air rises up and it cools down. Then the cooler, drier air falls, high pressure system. We're always going to see deserts at the 30s. There's going to be some other ways that we can form deserts, but common question on the AP exam is, where are deserts? The trick is to remember that deserts are not at the equator where the solar intensity is the highest. The reason? Because you're going to get lots of rain. Deserts are hot, but they're dry. So that's going to be at the 30s, where that hottest air has now dried out and falls back down. All right, some more questions. So you'll see those on the Ed puzzle. Another picture for you guys, just again, more descriptive, a little bit more time to sit with it if you would like to. Again, it's going to be in that slide deck that you can access underneath the calendar. So this is what it would look like if we could do a cross section, because the atmosphere is thicker at the middle of the spinning of the globe. It's a thinner atmosphere up north near the poles. Actually, the whole globe is thicker in the middle. Has a lot to do with gravity and dispersion and the speed. But you can see that in this picture. So you can see how the Hadleys are rising and falling. It also shows you the jet stream and the polar jet stream, which I think is just interesting because we do hear about those a lot in the news. So when we talk about the jet stream, we're really looking at that polar jet stream that comes down from the 60s sometimes, and then it dips down. All right, and our last big topic to think about is the Coriolis effect. And this is why some people say the toilets flush backwards in Australia. And they don't, but the ocean goes backwards in Australia, and the air goes backwards in Australia, just not the toilets. All right, so what is it? It's an apparent deflection of an object's path due to the rotation of the Earth. As the Earth rotates, its surface moves much faster at the equator than in the middle latitudes and the polar regions. So think about it, that you got to make a way bigger circle at the equator than if you are at the poles. So the Earth's rotation is faster. If you're thinking about going to physics, if you think about the radial speed versus tangential speed, we know that they're different. So you're going a lot faster if you're at the equator. The faster rotation found closer to the equator causes objects that are moving directly north or south to deflect, because we know from physics that you get your initial velocity from where you started from. So this happens with our winds as well. The prevailing winds are produced by a combination of the atmospheric convection currents, those Hadleys, ferals, and polars, and this Coriolis effect. So not that this is going to make a whole ton of sense to you right now, but I do have a couple videos that hopefully help.
slightly, I'm going to rotate the merry-go-round counterclockwise. But you throw it whilst it's moving. What's going to happen?
I don't know why, but I feel like if we're going fast enough,
Yeah.
like I might actually be the one catching the ball.
Okay, so you're going to throw it and you're going to catch it. All right.
Yeah.
What's going to happen? That's going to veer off to the left. So the ball is going to swerve off to the left. Yep. And you might catch it. Possibly. Okay, good. Right, so what's going to happen?
I think it's just going to come straight to me and I'm going to catch it like a champion that I am.
Show me the catch. Okay, good. Right, okay, so everyone, no, hang on, one more.
It's not arrogant.
Just quietly confident. Really?
No.
So what's going to happen to the ball?
I'm catching it. It's right here.
Great, so we've got 1 second to go off to you. 1 second comes to you, Spencer. And you think it goes straight, but you think you'll be the one catching it.
Yeah.
Now remember, the ball will be thrown straight across the spinning merry-go-round, but where will it end up? Will it be caught by the thrower? Will it be caught by the person opposite? Will it be caught by the person to the thrower's left? Or by the person to the thrower's right?
All right, and that's just a little quick check to see what you guys think. I'm not going to put that on there. Let's see.
Right, in your own time, throw the ball. So the answer was D. It was caught by the person on the thrower's right. But camera angles seem to show the ball bend in the air. So is that a camera effect, or are we seeing what they saw? Hang on, this couldn't get much more simple. The idea was just to throw the ball straight to Victor to show us his amazing catching skills.
Right. Yeah, it did. It just curved right over this way.
So let me get this straight. So you threw the ball, it left your hands, and then what?
And then it just got sucked over to him.
In the air.
Yeah. Perfect throw.
What did you say?
Yeah, curved right in.
Right, so we all agree here the ball curved in midair.
Yeah.
And you didn't cheat this at all?
No, I didn't.
Okay. And do you know why it did that?
No.
No idea. It's called the coriolis effect. It's very simple. It's objects in motion appearing to be, it's an optical illusion, appearing to be deflected off their intended course. So what's actually happening here is you are throwing this ball. You can only throw a ball in a straight line. Can I clear that up straight away?
Yes.
Even though it appears in your eyes to be bending. So you throw the ball straight, it's still going straight, but the table is moving below you. And all of a sudden, look who's in front of that straight moving ball, and it looks like it's bent off to the right because you're still looking at the guy you were intending to throw to, and that, ladies and gentlemen, is a coriolis effect.
All right, so hopefully with that in mind, this kind of makes sense now. So if we look at these two pictures, a ball thrown from the North Pole toward the equator would be deflected to the west. And if we were down at the South Pole and we threw up towards the equator, it would also be deflected towards the west. So we're always going to be deflected because of the Earth moving in that same counterclockwise rotation. However, things are going to get a little bit tricky because we're going to see the interplay here with the Hadley cells. So I want to start this off by just saying, there's your overview, there's your basics. And then what we're going to really look at is that space right by the equator. And I want you to look in picture B. I want you to look at just the area between 30 and the equator. It can be north, it can be south. And you see that for both of these, the deflection is to the west. The problem that I have here, and that students have had, is the way that the questions can be worded can be tricky. You will see some people say that if I were walking towards the equator in the northern hemisphere, I'm deflected to the right. And if I'm walking towards the equator from the southern hemisphere, I'm deflected towards the left. I don't like using that language. It feels like too much to remember. Just remember that you're always deflecting to the west. So westward deflection as you head towards the equator because the Earth is spinning towards the east. Okay, so that's the first step, is just look at what's right by the equator. Then things get a little bit trickier because it makes a circular pattern. And so this is easier to see in the southern hemisphere. That first I'm deflected up and to the west, and then pretend like you're following that around to make a full circle. And we'll see that the surface winds that are down in that next section, the ferrule cell, the surface winds are the ones that are going to be going to the east. So what's happening here? The deflection is the same, but we are only concerned with the wind at the surface. So that's the tricky part, is we want to know what's happening at the surface. Remember that at the equator, all that air was rising up. So we were talking about the air that's getting sucked towards the equator, but then all that air is falling at 30. So we're talking about the air that's being pushed out at the 30. That's on the surface now. It's a lot that's going on right here. And I'm going in probably into a little bit more depth than you need, because some of you will want that to make sense of it. All right, so we put it all together, and we'll do this in review when I get back. Is we will put together a diagram that really goes through this, but this is a great picture to have. If you want to print it out from the notes that are online, if you want to sketch it, pause the video. But what we're talking about here, again, the Earth is spinning towards the east. Sunrise is in the east, and then it sets in the west, so we're going around that way. The coriolis effect is creating that apparent drag at the equator. So we have the first winds are our trade winds, and they're the ones that are under the Hadleys. So that surface wind on the Hadleys, those are the trade winds. Now we have the northeast trade winds in the northern hemisphere and the southeast trade winds in the southern hemisphere. Then we just go with the westerlies. The westerlies are what's underneath the ferrule cells. And then we get the polar easterlies, and those are underneath the polars, so 60 to 90 degrees. So a lot going on in one picture. So you see the Hadleys, the ferrules, the polars. You see the direction of the surface winds. That's going to come back up too when we study El Nino. All right, and this is a prettier picture, putting it all together, showing you and labeling those trade winds for you, and also those westerlies. And really, we're looking at the tropics as kind of that ITCZ, the place where that's cutting off. We talk about it being 30. It's a give or take of a 30. 30 is a number that you do see in the AP exam, though. I'm not making that up from nowhere. The winds are named from the source direction, where they come from. So the northeast trade winds are coming from the northeast. It's a really weird thought, because when we're trying to draw that arrow, we want to draw it like it's a compass needle. But no, it's coming from the northeast. The source of the wind is the northeast. So the northeast trade winds are the ones right above the equator. Westerlies come from the west. Polar easterlies come from the poles, and they come from the east. All right, love this picture, but this is one of the reasons I was going to do it as a Nearpod. We struggled with this though last year virtually, so I know that would be a struggle again. But when I come back, we are going to work specifically with understanding how this all fits together in a nice little picture. So that's it. Hopefully you understand kind of what's going on, at least being able to understand those convection cells, how the air is moving, not necessarily yet grasping every single one of those vocabulary terms, but knowing that you'll need to go back and study those. So thanks for watching, guys, and I hope you did well.